Okay, here we go. Getting down to it. Father, thank you for today. Help us to learn these things, to get through them in a timely way, and to recall them, and to prepare for our tests, and for all that the future holds. We pray this in Jesus' name. Amen. All right. I've got like 3 markers in the whole place. All right, tell me the last problem we did. Did we start our, I think I know which one. I think we're on determine a solution of 4 grams of a non-electrolyte dissolved in 55 gallons. Did we do that one?
Yeah, we did the one that was the opposite. That we had to find the moles, and then we had like 4 grams of unknown, and then we find the moles.
Okay, so we did that.
Yeah.
Did we do the follow-up to it?
Yeah, we did two.
Okay, good. All right. Then we have determination of molar mass from osmotic pressure. So this is 11.12. It says a 0.5 liters of an aqueous solution containing 10 grams of hemoglobin. Did we do this one?
Yeah.
We did this one. Well, what am I on here? My goodness. Did we do the follow-up to this one?
Which is the...
We didn't do the follow-up to this one.
Yeah, I think this was the last one. I remember the
Hold on, where? Okay, all right, let's do the follow-up. Assuming ideal solution behavior, what is the molar mass of a protein if a solution of 0.02 grams of the protein in 25.0 milliliters of solution has an osmotic pressure of 0.56 torr at 25 degrees centigrade. Okay, so we got to go back to how we find our osmotic pressure, right? Osmotic pressure equals what? Do you remember?
MRT.
MRT. So capital M, molarity, R, ideal gas constant, and T. And what value are we using for R? 0.08. Go back. This is not the version that I have ingrained in my heart and soul. Come on. 0.08206. Okay. And T is going to be in absolute temperature, so right away we know we need to take 273 well, we will skip the 1.15 because the book keeps doing that, and we'll just add 25 to it, so 273 plus 25 is 298 degrees Kelvin, right?
Yep.
Okay, so what are we trying to do with this problem? Assuming ideal solution behavior, what is the molar mass? So we want to find molar mass. We're going to do that by solving for molarity, I assume. So we have 0.56 torr equals M times 0.08206 times 298 degrees Kelvin. So we'll divide this by all of this, but we need to convert this 0.56 torr into atmospheres. So we're going to take 0.56 torr, divide it by 760 torr. That'll give me my atmospheres. Then I'm going to divide that by 0.08206 times 298 degrees Kelvin. And this is going to give me my moles per liter. Let's both do the math on this, because sometimes one or the other of us will mess up. just did right there. Ooh. See something like that?
Yeah.
3.01 times 10 to the negative fifth. Okay. So this is 3.02 times 10 to the negative fifth moles. I've got to have a better thing than this. Moles per liter, right?
Yeah.
Okay. Now, I have 0.02 grams in 25 milliliters solution. So the first thing I can do here is I can multiply this by 0.025 liters, and that'll get me the number of moles, right?
Mm-hmm.
So let's go ahead and do that. I just lost everything. Okay. So we got even smaller, right?
Mm-hmm.
So this will give me moles. I've got like 7.53 times 10 to the negative 7. You got something about like that?
And -6.
Negative 6.
Mm-hmm.
Okay. Let's both run it again. Well, no, that time I get to the negative 7 again.
Okay, I see what I do.
Okay.
It's 0.025.
0.025.
Yeah,
Yes.
I put
Okay.
0.25. Yeah, -7.
Okay. All right. So this is moles, right? So I know that I'm sorry, let's go this. I got 7.53 times 10 to the negative 7th moles has a mass of 0.02 grams. Right? Okay. So my molar mass is going to be mass per mole,
Mm-hmm.
right? So all I need to do is divide this by, that's not going to be that, right? Yes, it is. Okay, I need to divide that by that. Okay, so molar mass equals 0.02 grams over 7.53 times 10 to the negative 7th moles. Okay, so I get 0.02 divided by 0.123456753 equals huge 26560 grams per mole.
Yeah.
Not unheard of for protein though. What do they get? 3 times 10 to the 4th. Yeah, that would round up to that. Okay.
Mm-hmm.
All right. Good enough for them. Good enough for me. Okay. Next step, I think, is stuff we already did. They just did it later. The dissociation. And they finished today yet, which would be nice.
Mm-hmm.
Okay. Colligative properties of electrolytes. As noted previously in this module, the colligative properties of a solution depend only on the number, not on the identity of solute species dissolved. Concentration terms in the equations for various colligative properties, freezing point, depression, boiling point, osmotic pressure, pertain to all solute species. present in the solution. For the solutions considered thus far in this chapter, the solutes have been non-electrolytes and dissolved physically without dissociation or any other accompanying process. Blah, blah, blah. Do we actually care about this? Okay, considering the solution is actually prepared at freezing point pressure measured, however, the value of 3.4 degrees centigrade is obtained. So discrepancy observed for all other ionic compounds, and differences between the measured and expected colloidal property values typically become more significant as slate concentrations increase. These observations suggest that the ions of sodium chloride and other strong electrolytes are not completely dissociated in the solution. To account for this, and to avoid the errors accompanying the assumption of total dissociation, an experimentally measured parameter named in honor of Nobel Prize winning German chemist Jacobus Enricus Van Hoff, that's a lot, is used. It's called Van Hoff's factor. It's little I. That's a dead marker. And I'm making out markers. Somebody's been stealing my markers. I'll be right back. Let me get some marker. She says they don't all work, but that can happen. Okay. Okay. So little I, iota in Greek, is Van Hoff factor. It's defined as the ratio of solute particles in solution to the number of formula units dissolved. Okay, here, what are we saying here? This equals moles of particles over moles of formula units dissolved. Why are we doing this? Why are we caring? Because while we expect theoretically that if I put a bunch of sodium chloride in a solution, it's all going to dissolve, and I can go, okay, I put 2 moles in, so I've got 2 moles now of species, and therefore it should depress by this amount. That's theoretical yield, but it's not ever coming out the same, and they're noticing that this is consistent across all different ions, so they're come to the realization that yeah, it all dissolved, but it didn't all separate. Some of it is remaining together. And so that's what this is about. Okay, so let's keep going from there. Values for measured Van Hoff factors for several solutes, along with predicted values assuming complete dissociation, are shown in the table below. So you have to do this for each different molecule. All right. In 1923, the chemists Peter Debye and Eric Huckel proposed a theory to explain the apparent incomplete ionization of strong electrolytes. They suggested that although inter-ionic attraction in an aqueous solution is very greatly reduced by solvation of the ions and the insulating effect of the polar solvent, it is not completely nullified. The residual attractions prevent the ions from behaving as totally independent particles. In some cases, a positive and negative ion may actually touch, giving a solvated unit called an ion pair. So one thing that we see here is we may even have ion pairs. Okay. Thus, the activity or the effective concentration of any particular kind of ion is less than that indicated by the actual concentration. Ions become more and more widely separated the more dilute the solution. Okay. Thus, in extremely dilute solutions, the effective concentrations of the ions and their activities are essentially equal to the actual concentrations. Note that Van Hoff's factors for the electrolytes in the table that we're skipping but we'll be addressing are for a 0.05 molar solution, at which concentrations the value of I, say for sodium chloride, is 1.9 as opposed to an ideal value of 0.2. So with just a 0.05 molar solution, you're already down a tenth. Okay, so freezing point solution of an electrolyte. The concentration of ions in seawater is approximately the same as that in a solution containing 4.2 grams of NaCl dissolved in 125 grams of water. Use the information and a predicted value for the Van Hoff factor to determine the freezing temperature of the solution. Okay. All right. So we've got 4.2 grams of sodium chloride. What are we trying to find here? Find the freezing point. We're going to find the freezing temperature. Okay. All right. So we have 4.2 grams in 125 grams of water. Right. And so we're going to find our molality. Right. So 4.2 grams over, we're looking at what, 23 plus 35.5. So this is 0.07 moles. Yeah. And we want to find molality, so it's 0.07 moles over 0.125 kilograms. That would give me 0.574 molality. Okay. Okay, so now I can take that, I think, and use the chart that they give us for sodium chloride. So, Van Hoff factor here looks like it should be about 1.9. Wait, is that right? That's for 0.05. I've got 0.5. I did not work out this problem in advance. So convert to grams of mole to moles of sodium chloride using the molar mass. We did that, we got 0.072. Determine the number of moles of ions present in solution using the number of moles of ions in 1 mole. So we should get, according to this, 0.14 moles of ions. Then determine the molality of the ions in the solution. Okay, so this is going to actually, should double, right? So they say, all this is basically going to double, so I will get 1.2 molality. Use the direct proportionality between the change in freezing point and molal concentration to determine how much the freezing point changes. Then determine the new freezing point from the freezing point of the pure solvent and the changing result. Check the results. This is self-assessment, taking care to avoid rounding. Oh, goodness. See how it maps. .2 molal. I don't know how they're getting, where they're getting. Wait, this does not make any sense. You will not have a problem about this. And when I give you a problem using an ionic species, we will only use it for boiling point. We won't use it for freezing point. Or if we do use it for freezing point, I will say theoretical.
Okay.
In all my years of science, I've never come across the Van Hoff factor. I have to imagine it's there somewhere in one of the textbooks, but I've never used it. All right, so here we go. Colloids. We didn't care about colloids. Giving problems with colloids. Do you know what colloids are? Essentially permanent suspensions. So it's somewhere between a solid and a liquid. Think of something like a gel or a jelly, right? So it is capable of flow very slowly, but it's so if I have dirt and water and I shake it up, right? Like what I'm dealing with there is a suspension, but of course the dirt's going to fall out of suspension. With a colloid and the nature of the species that are in it, it doesn't fall back out of suspension. It just remains that way.
Like mud.
No, not like mud.
Because it's one thing.
Like jelly.
Okay.
Or like jello, or like gel, where it's actually going to hold this
This form.
this form. So, and like I said, they give you no problems on it whatsoever, and I'm not going to ask some nonsense theoretical questions. So I actually think we are done. We've covered all the material we're going to cover. So, I sent an email out to everybody else, but you haven't got it yet. The test will be available Thursday.
Mm-hmm. This Thursday.
Yep, and you'll have until Wednesday to get it done, next Wednesday to get it done.
Mm-hmm.
So, yeah. question was, well, what am I doing for a final exam? Probably, I'll send out an essay, but it'll be nothing crazy, nothing too hard.
Okay.
All right?
So we're gonna have test 4 and then ISM.
Yep. And then graduate.
Sounds good to me.